Okay, dear faculties and students, we are very glad that Professor Johnson can visit us today. We feel very happy and honored you can come to our university again. I remember you were here several years ago. Yeah.
10 years.
No. 10. We had a dinner with you.
2 or 3 years ago, right?
Yeah. We had a dinner with you. Yeah. We had a dinner with you and Professor Cho. HR Cho, but he retired already. Yeah. Yes. So we are very glad that Professor Johnson can come here, and so I would like to present you a small gift. Okay. Hello, stop.
Okay, good.
Okay. Stand.
You can send email to here.
And
the mail.
And a t-shirt. Exercise. Okay. So I would like to invite Professor Lin to give an introduction about
I'm happy to introduce Professor Johnson. Professor Johnson joined the Colorado State University Department of Atmosphere after complete his 2 years faculty at the University of Wisconsin. After that, he served as the lead scientist in the international experiment, Coca-Cola and SysMac. Actually, he also very close joined our first international experiment, that is the 10MAX. So since then, he became our good friend. So he visited here several times. I think 4 or 5 times, right? Okay. Yeah. Professor Johnson get many honor from the academic institute. Like he is the fellow of AMS, American Meteorological Society. He is the fellow, and he is the UCA Board of Trustee and co-chief editor of the Journal of the Atmospheric Science Advisory Committee and the Clever Monsoon and Pacific Panel and the Clever Working Group. NSF Special Creative Award he get it from 2003 to 2005. And his research interests include meteorological convective system and tropical convection and monsoon process. So today he will give us the new discovery and future challenges. We also invite him to give a very short review of the past 50 years tropical meteorology development. And from this point of view, I think you will give a very interesting and a very valuable review for the tropical meteorology. Let us give a great
Well, thank you very much. It's a great pleasure to return to NCU and meet friends here. And I came actually to help plan a new experiment, CAMX2 it's called, proposed for 2008. And I'm representing the U.S. scientists who are getting involved in this experiment, and we're having to work real hard now to get this underway. So I'm going to give this talk here on tropical convection. You mentioned the history. I may be able to say a few things about that later, if there's time, I had a PowerPoint, you haven't loaded that one up, but if I cover that, maybe we may have to load on, and just hit with some of the highlights, if you like. So this talk deals with tropical convection, where there's some new findings coming out, and of course, all the time. And one of the, and we'll see at the end here, there's some new results coming out from new satellite, in particular, a satellite called CloudSat, which is measured. It's a millimeter cloud radar from the satellite. It's measuring new fascinating statistics about the global cloud distribution. So, but first, I'd like to say a few things about reviewing the subject of cloud systems. This is a diagram that shows the mean annual cloud cover for about 20 years from ISCCP over the globe. And the average cloud cover is about 60%. And the high values here are purple and white and so on. The cloudy areas in the eastern oceans, of course, show up in these kind of things, mid-latitude cloudy regions. And of course, in the tropics, we see cloudy areas in the Indonesian maritime continent and so on. And of course, the climate system is sensitive to cloud cover and cloud type. And there's conflicting evidence on the changes in the global cloud cover over the past 2 decades. Some have argued Cirrus is increasing a little bit. It's not quite clear. So this new measurements from space on clouds and Cirrus and so on are very important. And deep convection impacts the Cirrus cloud cover, so it's important to understand tropical convection. Well, a brief review of tropical cloud systems going back a number of years. This cloud systems have been studied. One main category of cloud systems we call the trade wind cumulus, shallow cumulus clouds, the most populous of all cloud types, seen everywhere in the tropics virtually, and have been studied for 3/4 of a century, going back to German expeditions and so on. And some of these shallower cloud types produce precipitation. It's been discovered in a recent experiment in Caribbean, RICO. They've studied the precipitation aspects of these cloud systems. So these clouds are prevalent throughout the tropics and subtropics. They're often in rows capped by a strong inversion. And they serve to transport water vapor vertically, balancing the drying effects of the large-scale subsidence in the subtropics that is ever present. Horizontal scale of these cloud systems is the order of 1 kilometer. Vertical scale, 2 to 3 kilometers as these grew up to about that height. With a short lifetime, just 10 to 20 minutes, and the precipitation process is predominantly a warm rain collision coalescence process, of course. And if you look at the fascinating high-resolution satellite imagery like NASA Lotus, you see these little clouds everywhere in the equatorial tropics. Of course, the other mode of convection that's important is deep convection. Has a horizontal and vertical scale, roughly 10 kilometers or so, lifetime 1 hour. And the primary precipitation process here is ice phase, involves the ice phase with grinding and collection of supercooled water on ice particles. So deep convection has been known, of course, a long time being important in the tropics. And it's been pointed out in a landmark paper now 50 years ago, actually, Real and Malkus, that these deep convected cloud systems are important in the energy balance of the equatorial trough zone. And they argue, if you look at the global tropics here, you have these Hadley circulations with low-level convergence along the equator, upward motion, and polar transport in the upper levels. It turns out there's a minimum in theta E, or more static energy, in the mid-troposphere. And if you consider the transports by these circulations, mean ascent would not accomplish the vertical transport that's necessary to balance the budget. Real models proposed that you needed hot towers or undiluted ascent in the tropics to satisfy the global energy balance. Well, there's a slight update to this concept by Zipser in 2003, where he provides evidence that undiluted ascent over the oceans is relatively rare. He's flown in many cloud systems, and they haven't seen these hot cores. They're very fact, it's very rare to see these. And he argues that freezing is actually an important source of additional buoyancy that allows the towers to go to higher elevations, and that this perhaps is a mechanism by which you can satisfy the energy balance, add to buoyancy in these deep cores, and they do not necessarily have to be undilute to make it to the tropopause. So this is an interesting idea, controversial, and further work is really needed on this. So the tropical cloud systems observed for many years have led to the concept of a bimodal distribution of tropical clouds, shallow cumulus and cumulonimbus. We'll take a closer look at this concept later, but first, let's look at some properties of these cloud types. Actually, these two cloud types are not independent. Go look back at the early work, pre-gate work of Yanai et al. And Eric Howard Schubert. They pointed out that these shallow clouds moisten the atmosphere to assist the growth of deep convection. So you might have a population of clouds where the shallow clouds are growing and detraining, moistening, and providing an environment that helps favor the growth of yet deeper clouds. So shallower clouds can affect deeper clouds. And Yanai et al. And one of the authors of this paper right here, is that correct? Showed that with Marshall Islands data that there's the detrainment moistening from these shallow clouds in the lower troposphere. Well, in addition, deep clouds modify the environment and thus affect shallow cloud growth. For example, Yanai et al. Shows that there's subsidence drying in response to the deep convection, and so this drying could also affect the growth of the shallow clouds. So the clouds are really coupled together. Now, one of the new ideas that's come about in recent years is that this substance that occurs in the environment of these cloud systems takes the form of gravity waves that are generated by convective heating. And this is an example from the work of Brian Mapes showing heating profile in deep convection that has a top-heavy characteristic, which I'll describe later, which generates two modes of gravity waves that propagate horizontally away from the convection. So this is at some time after the convection has gotten going, and you have one mode that moves off very quickly that's related to a single vertical heating profile part of this total heating, and it's a subsidence mode that propagates away. There's a second vertical mode structure in this heating, which I'll describe later, that leads to a slower moving mode that propagates away with subsidence aloft, rising motion at low levels. So there are dispersive gravity waves coming out of this complex heating source. And this overall picture of heating, as shown here, can be better illustrated in this animation, a simulation, I should say, of gravity waves from a top-heavy heat source. This is by Rob Flavell at UCLA. And it's going to go through a second time. But you can see there's a heat source here, and it has a top-heavy profile, as I described. There's overshooting cooling in the, this is a vertical axis here, in the upper levels. There's warming. This red color means warming, and there's a rapidly moving warm feature associated with substance that moves away. And then there's warming above cooling that follows behind. This is that slower moving mode. So, and this moves away. So these, this top-heavy heating profile generates these two modes that move away from the source. And these modify the environment of the system. That this one warms the whole layer. This one warms this middle and cools the lower part. But Brian Mapes argued that this cooling the lower part can destabilize the atmosphere and help promote growth of convection near a previous source of convection. So we'll get back to that a little bit more later. But first, I want to say that frequently convection will tend to organize on a mesoscale, as shown in this diagram here, or this figure. And it's basically the wind shear that's critical. Let's see, but also the stability in the atmosphere is important. But we see examples of this organization in mesoscale convective systems, such as squall lines, mesoscale convective complexes, or blow aquas. So here's like a squall line, or above equal at mid-latitudes. This mesoscale organization has been identified going back actually to the Line Islands experiment in 1969, work done by Ed Zipser, but followed on by work done during GATE in the tropical eastern Atlantic by Bob House and Ed Zipser. And they found that these systems had an organized structure with a convective component, as shown here, trailed by a stratiform or lighter rain region behind it. These systems were found to be commonplace in the tropics, contain convective scale, mesoscale downdrafts. They enhance the surface sensible and latent heat fluxes over large areas. And they contain the stratiform anvil portion that contribute a significant fraction of the total precipitation, up to 40% or more. For these types of systems, there's you can break these overall mesoscale convective systems into two components, as I mentioned. One is a convective area, this idealized depiction, in a mature stage of the system. There's a convective area with updrafts and downdrafts. There's a mesoscale area with what we call stratiform area with mesoscale ascent and mesoscale descent. These are profiles of the diabatic heating rates in the two regions. This is the convective region. There's heating at virtually all levels. Heating aloft by condensation and freezing, and heating at low levels by condensation. In the stratiform area, there's deposition heating aloft principally, and evaporation and melting, cooling at lower levels, melting near the 0 degrees sea level. So the heating profiles are quite different in these two regions. If you combine these two profiles together, you get this, what's called top-heavy. The peak and the heating distribution is in the upper troposphere. So the net heating depends upon the convective stratiform ratio, the partitioning between convective and stratiform component. And this heating peak that's shown here, it really shifts upward with time as systems mature. Early on, systems are mostly convective. They have this kind of heating profile, but later they may take on this, so the heating peak shifts upward with time. Well, what are the dynamical implications of these profiles of heating? We can look at those in several ways. One is through potential vorticity dynamics. We define potential vorticity in this way. We can write an equation for the time rate of change of potential vorticity. It's proportional to the vertical gradient in the heating rate, theta dot. So potential vorticity is created by vertical gradients in heating. And if we look at the two profiles for the convective and the stratiform areas, it's the vertical gradient that contributes to the heating rate. And where the heating increases with height, positive PV is created, potential vorticity. And so you have that occurring here at low levels in the convective area. The stratiform area is particularly pronounced at mid levels because this vertical gradient is extremely strong. So there's an impact on the potential vorticity field by the stratiform region. As these kinds of systems develop and mature and decay, often the stratiform area is left behind, and it affects the potential vorticity field. Here's an example of the impact of that. It turns out from that effect, mid-level circulations often develop, such as shown here. This is a mesoscale convective vortex, or MCV. There was a large convective system. This is the peninsula of Baja California. This is Mexico. A large convective system developed here, decayed, and left behind this mid-level circulation defined by mid-level clouds, and it moved off out over the East Pacific. We often see these over the central United States, and I've seen them over China and other places around this region. So another dynamical implication, there's something called spherical balance, and it can be applied to the ocean, and it's sort of a simplified form of the vorticity equation, where you have beta v is equal to f times the vertical derivative of the velocity, or f dw dz. Well, this beta is the latitudinal gradient of the Coriolis parameter, and W is proportional to the heating rate. So this right-hand side says if there's a vertical gradient in the heating, it'll affect the meridional flow, which is V. An example of the application of that is from the Eastern Pacific. This is from EPIC, an experiment in the Eastern Pacific. Here's Mexico. This is a north-south section. The equator's here. This is the ITCZ north of the equator. Well, it was discovered during EPIC that there's a meridional circulation shown by these red arrows with flow towards the ITCZ at low levels and a branch coming equatorward in the mid-troposphere. Well, this kind of a circulation might correspond to a heating profile that's rather with a shallow peak, because this vertical derivative changes sign in this area. If the peak in the heating is there, WDZ changes sign above it and below. And that could help support this meridional circulation. There's evidence that the heating peak in the Eastern Ocean is actually lower than the Western Ocean, and this is sort of consistent with this shallow meridional circulation that's been found. And that's been reported by Shidong Zhang in a recent paper. Other dynamical implications, there's impact on the east-west Walker circulation. The study by Hartman, Hendon, and Howes showed that if you apply these idealized profiles of heating, one in the upper troposphere, one peaking in the mid-troposphere, and look at the east-west circulation along the equator, you get two different structures to this circulation, east-west circulation or Walker circulation. So the Walker circulation, as well as the Hadley circulation, is influenced by the vertical distribution of heating. So it's important to get that right, for example, in numerical prediction models. Now, I've already mentioned these gravity wave modes that disperse away from heating. If you have a heating profile, convective and stratiform, combine it together, you get this total heating. This combined heat source generates these rapidly propagating modes. This one goes away at 40 meters per second, this at 20 meters per second. And this rising motion near the source, mates argue, may promote new convection, and that's an interesting area of that's a study that's being explored. So within an overall squall system, there are really a hierarchy of convective elements at various stages in their life cycles. It's not so simple as just having convective and stratiform. You have all kinds of clouds at different heights and so on. And for future reference here, I'm going to refer to the clouds that grow to the mid-levels as congestus clouds, because it turns out I'm going to discuss these a little bit. So what is the overall population of convective elements? Well, if we go back to a paper by Howes and Cheng in Gate, where they used data from the radar on the ship oceanographer, they followed the growth of clouds, precipitating clouds, okay, and recorded the maximum echo height, and then plotted histograms of the echo height for 3 different phases of Gate, each about 3 weeks long. So these are the histograms. This is height, and this is the frequency. And you can see that there are peaks in these at the 2 to 3 kilometer point. These represent lightly precipitating trigon cumulus. However, there's also peaks here around 6 to 7 kilometers, or 5 kilometers, 5 to 6, or 7. And these peaks are related to clouds that grow to a little bit higher elevation, cumulus congestus clouds. This work has been followed by a study based on total core data. Total core was conducted in 92 to 93 for a 4-month period over the Western Pacific. And we used data from the MIT radar aboard the ship Vickers. And we, in this study, which was published in 1999, we also did a analysis of the frequency distribution of echo features. We call them convective features. And this is the height of them and the frequency. And there are a lot of curves on here, but just pay attention to the yellow one. So this is only for precipitating systems. We found a peak at about 5 kilometers here in the frequency of echoes. So this is the echo top frequency distribution. It turns out this is a plot of the rainfall distribution. It has a peak for higher convective feature heights. And this means that the taller convective features contribute more rainfall, and that seems to make sense. This frequency distribution here does not have a peak in the deep end of the spectrum. You would expect lots of clouds growing up and spreading out in the annuals. Well, it turns out the cumulonimbus clouds are undercounted because these annuals tend to merge together, and there may be lots of turrets that grow up, but you get one annual, so you count that as one, whereas there may be many towers involved. So we know that we're undercounting these. We also know that there are non-precipitating cumulus clouds at the low end here, and they're not measured by the precipitation radar. Anyway, there's one peak showing up here. These congestus clouds, if we define them as echoes with tops between 4.5 and 6 and 9.5 kilometers, they're the most abundant precipitating clouds in core, accounting for 57% of the population. The cumulonimbus produce the majority of the rainfall, shown here, but congestus still account for over a quarter of the total rainfall. So, as opposed to bimodal, there's evidence of what we call a trimodal convective cloud distribution, and that's roughly illustrated here. We have convective height, feature height here, and then there's a log for frequency distribution, and these are populations within the radar area. Now, the precipitation radar can't detect all of the non-precipitating clouds, so we've counted them in other ways. We've used data from aircraft, the work that Peggy Lamone has done, and estimated two different populations of cumulus clouds. But regardless of what you use here, the populations of little clouds are enormous compared to the congestus peak down here. And then we have an undercounted cumulonimbus population. So these three features seem to stand out in the total core data. So that led us to put together this sort of idea of the tropical cloud populations for the total core period going from 30 north to 30 south. We have what's a sort of a trade inversion that actually extends across the equator. You have trade cumulus clouds with some overshooting. There's a melting layer here, and there are clouds that grow up, and there may be some shelf clouds at the melting layer, but these clouds overshoot a bit, and then you have the deep convection. So this is sort of the trimodal cloud structure. Well, these congestus clouds are really nothing new. They've been studied for many years. If you go back to 1957, there were flights across the Pacific by Reel and Malkus. And this is Joanne Simpson, at that time Malkus, studying these photographs of the clouds from as many flights, very tedious thing, and looking at the height distribution and so on. She was a graduate student at University of Chicago in the 40s, and she worked under Rossby. And she was talking to him about what type of research she should work on. And this is from an autobiography. She says, "So I was interested in clouds for just themselves because they were fascinating. Rossby said that no one was very interested in them, so it was a good subject for a little girl to study." Anyway, she made a lot of hay with the cloud system studies. Okay, so more recent observations. These is from a millimeter cloud radar at Manus Island in Equatorial Pacific. This is from a paper by Hollers et al. For about a year. They determine cloud top heights, and this is for many cases. These are millimeter radar-derived heights. So this is height here and the number of cases here. So these are histograms. And this is day and night. This is the same thing, trying to estimate it from GMS satellite, day and night. Well, you can see the sort of trimodal distribution of cloud top heights. This one, mid-levels, is actually much weaker. However, I'll talk about the significance of it a little bit later. If you look down from satellite, you can't pick out this middle layer. And also you get the tops of clouds in correctly from IR kinds of information, of course. But the upper level clouds often obscure these mid-level cloud layers when you just look at IR data. So why do we have this distribution of cloud tops that's trimodal? In other words, what factors influence the growth of clouds? These are photos taken from total core of some of these congestus clouds that grow up to mid-levels. They rain heavily, and then they die out. One factor is atmospheric stratification, and this is a diagram from Toga core. So this is a pressure or height here, and this is a 4-month time period. And what we've plotted here is dTdz, or the stability, basically, of the atmosphere over the central part of the core region. And if you, the warm colors here indicate higher stability. So you can see here, there's actually what's called trade wind stable layer along the equator in the core area. There's higher stability near 2 kilometers. There's also higher stability near 15 kilometers, and that marks the tropopause. But also there's a layer of intermittent higher stability near the 0 degrees sea level. This is the dashed line. So there's something about the melting layer that's increasing the stability. So there are possible causes for this stable layer are the direct effects of melting. When you have snow fall into the 0 degrees sea level, it melts and it removes heat from the atmosphere, and it's in a layer maybe 500 meters deep, and you stabilize that layer. And after the precipitation goes away, that stable layer is left around. It's a remnant feature. So that could create a stable layer over a large region if you have a lot of precipitation. Another effect is what Brian Mapes has referred to as melting layer convergence. From those gravity wave depictions earlier, there's evidence that there's mid-level inflow near the 0 degrees sea level into the equatorial intertropical convergence zone. And Mapes and Zuidema have shown that this can, there can be a radiative stabilization of this dry air that comes in, and that could lead to a stable layer. So stability is an important factor in affecting the growth of clouds, as we'll see more in a moment. But another, there's a possible factor. Another possible factor is entrainment drying. This is a time series of the relative humidity for Toga core, going for a 4-month period here. The colors are such that where it's red, the warm colors are dry. And this is a 0 degrees sea level here. So you can see there are some periods here where it's dry, and then it's moist, and then it's dry in mid to upper troposphere. It's generally, of course, very moist in the boundary layer. If you have cumulus clouds growing in an environment when it's dry at mid-levels like this, the clouds will entrain this dry air and have a hard time developing to higher elevations. So this mid-level dryness can hinder the growth of congested clouds. So that's a possible mechanism for restricting the growth of convection during certain periods. There's a convective period right in here that occurred during Toga core in mid-December. And this was associated with an active phase of the Madden-Julian oscillation. So there was extensive deep convection at this time. So there was there's a heat source. And this is a diagram from the work of Gill, which considered a heat source along the equator right here. So this is north-south, this is along the equator. And he looked at the response of the atmosphere to an equatorial heat source. And this is the low-level flow response. It was found that off the equator, to the rear of the heat source to the west, there were these Rossby gyre circulations. And there was flow towards the equator behind this system, and then flow towards the heat source behind it, which led to westerly wind bursts. Ahead of it, there was a flow toward the heat source. In the vertical, there was rising motion in the heat source area. This is a vertical cross-section, so it's moist in there. But out ahead, there was sinking, and out behind, there was sinking, and so it was dry. If you look at the structure of the time series for Toga core, you can see this moist and dry pattern where you have the heat source at this point and it's dry actually out in advance of it, or an earlier time here, and behind it there was a dry air region at mid-levels also. Now, a dry period here that occurred before this one was studied by Ringel-Sperger et al., 19 November 1992. And they considered this dry period and the cloud growth during that period. They looked at cloud resolvent modeling results for this period, and it's about a 5-day period. And this is height here. They found clouds would grow up to about 6, 7, or 8 kilometers only. And they, from their modeling results, showed that inversions near the melting level and entrainment of dry air limited the growth of convection, with water loading being a secondary effect to limit the growth. And these are observed cloud tops here and the simulated rainwater, also showing clouds, growing up to about 6 to 8 kilometers. They found that the reduction of buoyancy through entrainment made the stable layers more effective in stunting the cloud growth. So that was the result of their study. So it's both entrainment of dry air and this sort of stable air are helping to limit the growth of clouds. Well, what about these cloud systems in the context of the Madden-Julian oscillation? This is a satellite image showing a large convective region over the maritime continent that's associated with the MJO. And Madden-Julian looked at the global context of the MJO and the deep convection that develops with it over the Indonesian maritime continent and Western Pacific. And behind this system, you see westerly wind bursts feeding into the deep convection. This is a figure showing, again, relative humidity for Toga core, but it also has a zonal wind on it. And here is the westerly wind burst that occurs after the deep convection. This is a moist period deep convection. If time increases to the right, so after that, you get this westerly wind burst. Okay, so that is the consistent with that model of Gill. But preceding this westerly wind burst is a period of light wind right in here. And this is when the atmosphere is very dry at mid-level, so convection has a hard time growing. If you look at that period, you see this is a photograph from Jianyang Hong number 5. The ship, one of my students, Jin Lin, was on this ship. He took this photograph. And it was just glassy seas. And you can see here are these shallow cumulus clouds growing up. This was a time animation of the visible GMS imagery over the Toga core IFA. It's 2 by 2 degree squares here. During the daytime, of course, we're seeing these shallow clouds that are developing over this region, similar to the region where the photograph was taken. And what you see here is sort of mesoscale organization to the shallow cloud, because in fact there are what's called open cells in here, or it's called also Bernard cells. It turns out that on these light wind days, the upper ocean heats, has been studied by you, by several degrees C, and there's a diurnal cycle to convection, and it gets enhanced in the afternoon. And on the perimeter of these cells, deeper clouds can develop. So this can force these congestus clouds during these light wind periods. And these cells have the structure something like this, where there's rising motion on the edge and sinking motion in the middle. And there's roughly 30-kilometer diameter to these cells. So there's a diurnal cycle that's actually probably important in developing these kinds of clouds during the light wind period of the Madden-Julian oscillation. So actually we studied the development of these cloud systems through the life cycle of the MJO during Toga core. And what's shown here are time series of the populations of cumulonimbus clouds, congestus clouds, and cumulus clouds. These are the shallow ones here, as a function of time going from November 10th to December 10th. This was before deep convection broke out. It was a light wind period mostly, although there was one disturbance here in around 25 November. It was a light wind period and dry in the mid-troposphere. And you can see here that during this period, the sea surface temperature is generally increasing. But there's also a large diurnal cycle in the SST here. except for this disturbed period. And you can see the populations of cumulus and congestus tend to increase. The cumulonimbus start to increase toward the end, but after this we have a diagram that shows they really increase, and then that becomes the active phase of the MJO. So there's a gradual increase in precipitating cumulus and congestus cloud populations. And the SST increases and has a strong diurnal signal, except for a brief interruption in late November. So there's a warming of the upper ocean. These cumulus and congestus clouds continue to grow. Here's the same diagram reduced in size that I had. And it shows these increasing populations of congestus and cumulus clouds. On the lower panel, we put in the relative humidity in the lower troposphere. And during this period of increasing cloud populations, you can see the humidity increases. So these clouds tend to moisten the lower troposphere by detraining and mixing out water and evaporating moisture into the lower atmosphere. And they precondition the atmosphere for deep convection. This is consistent with ideas about the MJO that have been referred to as a discharge-recharge theory. Blade and Hartman and Randall have argued that in the MJO you might have very active convection, it dries out the atmosphere, and then it takes several weeks to restore the moisture. But there's more to the story than that. There's dynamics. There's a lot of dynamics with the MJO, but there appears to be an important role of this mid-level clouds, low-level and mid-level clouds in moistening the atmosphere, preconditioning the atmosphere for deep convection. And the diurnal cycle is an important part of this process, including enhancement by mesoscale circulations. Because to get these congestus clouds, you probably need additional forcing by the mesoscale circulations to clouds. The clouds would grow a little bit higher than they would otherwise. So the diurnal cycle is probably an important part in this whole process. And if you want to get this right in a climate model, for example, you perhaps have to include somehow the effects of the diurnal cycle. So I'd like to then bring in more recent measurements from CloudSat. This satellite was launched last spring, and it's a 94 gigahertz millimeter radar. It's a nadir instrument, so it looks straight down. And this is an example of an orbit around one orbit here around the world. It's hard to see the terrain or the geography features, but this is Asia here, Australia, South America, and you can actually go to this just do a search for CloudSat, and you'll get to a website, and you can look at quick look data from CloudSat. It's available to everyone. So along this entire path, these are the clouds condensed down that exist. And here's the satellite going over Antarctica, so the lower boundary comes up here. Now, if you take one segment of this is 16 October 2006, like this segment right here, and if you click on the blue, you will expand out. This little cloud right here gets expanded out into this. So this is what it looks like on that segment, which is 1,400 kilometers long. This is a 30-kilometer height. So there's a convective system right there, and this is what it looks like from the CloudSat. Looking down from space, you have this deep convection system. The reflectivity is shown here. There's sort of a melting bed. Below that, you don't see much reflectivity. It turns out this radar attenuates heavily, so you don't see the precipitation going to the surface. There's a cirrus over here. When you see these clouds that grow up to mid-levels, these are the kind of congestus clouds that I was referring to. So that picture I just showed was actually along this swath southwest of Hawaii. It went through this convective system. So that's the context for that last one. Here's another swath of CloudSat through this system here that's mostly convection here, but there's a Cirrus that's flowing across here. This is India. And if we look at the CloudSat image for that, here's the path. You can see this Cirrus that I was referring to. Beneath that, you can see these clouds growing up here. So there's a lot of these around the world. It's fascinating to look at this if you just go on and click on these different areas to see the clouds all over the world. Now, here's one from 14 July 2006. I searched long and hard and I found the pass right over Taiwan. And this is the convection and cloudiness over Taiwan. Here's the lower boundary, here's terrain of Taiwan, Taiwan Straits, here's China. So there was a deep convective system over the Philippine Sea here, and this is the cloud structure of it. And there's convection, clouds over Taiwan, the height drops a little bit here. It looks like there's sort of these mid-level clouds over the Taiwan Straits, and then some deeper clouds in Cirrus over mainland China. Now, just recently, Graham Stevens and John Haynes have put together some climatology. This is for June, July of 2006, so this is very recent. They've sort of broken the clouds into three categories: shallow, middle, and deep. Look at the cloud tops now. So this is actually getting cloud top better than the precipitation radar, because the precipitation radar really can't get the cloud top. So this is much better at doing that. And these are shallow ones. Shallow ones are cloud top below 4.75 kilometers, the global distribution. So the red colors mean lots of clouds, lots of shallow clouds. And if you look at the stratocumulus regimes of the southeast Pacific and the northeast Pacific here and off South Africa, you can see that virtually all the precipitation that occurs in that region is from shallow clouds, and we know that to be the case. So this works out very nicely. If you look out at the Bay of Bengal and this area, there's very little precipitation from the shallow clouds. Of course, it comes mostly from the deep convection. The lower part here is deep convection, cloud tops above 11 kilometers, and you can see that in the Bay of Bengal, for example, the percentage of fraction of total rainfall from clouds with tops above this level is quite high, about 50% and greater. And this shows the ITZ regions in the East Pacific, Atlantic, and then the Indonesian maritime continent. But they did find that there were a number of cloud tops in the mid-troposphere, as shown in this figure here, throughout the equatorial regions. So they've developed sort of histograms here, or frequency distributions, for various ocean basins in the tropics: Indian Ocean, West Pac, East Pac, Atlantic. And this is very recent results. And basically what we look at here, like for the West Pac, you can see there are two curves here. One is the solid one for all clouds. The dotted one, or dashed one, is for clouds that just have precipitation in. They determined that. And the ones that have precipitation have peaks a little bit higher level because they are more energetic. But the structures are similar for both cloud categories. And you can see here, for example, the West Pac, there's lots of cirrus. Ones that are precipitating at higher tops. There's a general broad peak, although it's a complicated structure in the mid-troposphere, and then there's the trade-cumulus peaks. You see similar in the Atlantic. There's sort of this trigonal structure. Obviously, the shallow cumulus are very dominant. You can see there's much more cirrus in the West Pac than there is in the Atlantic and the East Pac. This is a really cirrus dominated region. And the Indian Ocean, whoops, is shown over here. It has a lot of cirrus in the Indian Ocean. This mid-level peak is less significant here. So the trimodal distribution observed, but it seems to be varied from region to region. Well, there are major challenges implied here. How do we treat the effects of all of these cloud populations in NWP models or GCMs? Can we increase the resolution of models sufficiently to explicitly resolve all clouds that exist? Of course, you'd need, probably have to go down to 50-meter resolution globally to do that. And it may be unrealistic to even think about doing that. With the Japanese Earth simulator, they've gone down to 3.5 kilometer resolution and are doing explicit simulations. And that's probably a direction in which things are headed. But still, there are needs in climate models to have coarser resolution because you have to have long time integrations. So if you have an area of clouds and you have grids in a model, of course these clouds cross over grids and in one region, clouds that develop may influence a neighboring grid square. And it's very complicated, and you have many little clouds. This is a big challenge. Also, there's another issue. If we go back to the total core results, where we have the various stages in the life cycle, sort of the developing stage of total core, when it's you have these shallow cumulus, deep convection. This is 17 days later. 9 days later, you have deep convection, shifting out to the dateline. But because of the large vertical wind shear, cirrus are advected over great distances. So what happened in one grid square in a GCM in terms of the cirrus clouds may be a function of convection 1,000 kilometers away. This is a real challenge. So how do we tackle this problem? Well, one approach is to use convective parameterizations, and many, of course, the main global models, operational models, are using perhaps one of these well-known models: Benson, Quo, Kane, Frisch, Erlkauer, Schubert. Another approach that's being considered is to embed a cloud-resolving model, 2D or quasi-3D, within grid areas of GCMs. So you have a grid area, and you put in a cloud-resolving model in there and try to predict the actual cloud development, and then incorporate that into the global model. This is sometimes referred to as super parameterization. The other approach is to explicitly resolve all convection. And recently, there's been an attempt to try to do that. As I mentioned, the 3.5 kilometer mesh aquaplanet model, they tried to simulate the MJO characteristics here. But there are deficiencies. With a 3.5 kilometer grid, you really can't resolve the convection right. So that's, you don't get the convective corridors and so on. So it's still been necessary for many applications, climate simulation, to use coarser grids. They do not explicitly include all cloud types. So alternative approaches will always be needed. So there are a number of challenges for parameterizations here that I'd like to mention. These shallow cumulus and congestus clouds are important, moistening the atmosphere, preconditioning for deep convection. They also will affect the radiation budget, because this moistening will affect the radiating field. There are these stable layers that may affect convection, and they're very shallow. For example, the trade inversion is has a small vertical scale. You might need high vertical resolution to capture that right. Mesoscale circulations can influence shallow cloud fields, and the diurnal cycle is important. And MCSs and their effects spread across one grid box to another. So to summarize, the point I'm making here is shallow and deep cumulus clouds are abundant, but a third population here, called mid-level clouds or congestus, yields this trimodal distribution. And it seems to be confirmed with the CloudSat data. Although the data are preliminary, it's still, we expect many more years of data to come in on CloudSat. Shallow cumulus and congestus serve the role of preconditioning the atmosphere for deep convection. Mesoscale boundary layer circulations enhance the congestus populations. Convection organizes on the mesoscale. This organization has local and large-scale dynamical impacts, and representing all cloud types and their complex effects remains a challenge for the treatment of convection in NWP models and GCMs. Well, thank you.
Thank you. This is a distinguished talk. Any comment, President?
What will be the lifetimes for the Cirrus clouds, and what would be the process to control the lifetime of Cirrus clouds?
Right. It looks like from CloudSat, and of course we've known this from before, that many of these cirrus clouds exist in the Western Pacific and in the Asian monsoon region. That's more so than the Atlantic and the Eastern Pacific. And I think deep convection is generating these Cirrus outflows. Now, what determines the lifetime? It seems that the lifetime of Cirrus is actually a lot longer than people had suspected. These ice is lasting a lot longer, and there's a lot of controversy about how is this happening. And so convection can go away, and the Cirrus can last a day or so. But also, there's recent evidence that indicate that Cirrus can be generated by stratospheric gravity waves, Kelvin waves, where you have a cooling in the lower stratosphere, or you have a tropopause, and it actually from these propagating Kelvin waves, and as they come to a region, you can cool the atmosphere enough to form Cirrus near the tropopause, and it's apart from any deep convection. And there's also the issue of very thin Cirrus versus opaque Cirrus, and there's a whole range of Cirrus that's out there.
Just saying that it can be of brand of damage too. So it's one of your solutions. So it come up for me to kind of ask you the question: what would be the advancement of the tropic meteorology and the relationship with all the very famous field experience, like gate, all this, how all those field experience contribute to the advancement of the tropic meteorology? Can you sort of give a short review on this kind of things?
Okay, well, you asked about TAMX2, right?
Related to.
No, I say
You're asking about all of these experiments.
some of not all of those. But
Okay.
like gate or
Yeah.
or how
Well,
they contribute.
Actually, it turns out a short time ago I gave a review talk on 50 years of progress in tropical meteorology. This is because the University of Hawaii had their 50th anniversary this fall. And so I prepared a talk summarizing this advances in tropical, going back to the 40s actually. And some of the early work was really Herb Reel, who got things started. And so I actually will have a talk is decade by decade. And there were, of course, experiments very early on the shallow cumulus going back to the 20s. And this is reported in Reel's famous textbook in tropical meteorology. But the active experimentation really began in the 60s. And this was a program we called GARP, really, that motivated this. And Jewel Charney was one of the key people that got GARP going. He realized that to improve global forecasting, you really needed data from the whole world. And we needed some kind of an experiment to increase the data, including the tropics. The tropics were often ignored by mid-latitude meteorologists. And so GARP began in about 1967. And as a precursor to this global experiment, which ended up being called FIGGI, they had several smaller tropical experiments. One of them was BOMEX, Barbados Oceanographic Meteorological Experiment. Another was ATEX, Atlantic Trade Wind Experiment. Another was the Line Islands Experiment. These all took place in the late 60s. And they were of fairly small scope, but they were significant. And there were some important results that came out there, like Zipser's work on MCSs. That really came out of the Line Islands Experiment. The structure of the boundary layer, ATEX, some important results, tropical boundary layer, the trade cumulus layer. And BOMEX, there were some very important works on even heat budgets for the trade cumulus, work done by Nita and Esbenson. And then after that came GATE, the GARP Atlantic Tropical Experiment, which was first proposed to be in the, actually the Western Pacific. That's, although the acronym would have been harder to pronounce, GARP Pacific Tropical Experiment. But it turns out the resources available to the Pacific were not as much as the Atlantic. In particular, for example, the ships from the Soviet Union were not available to go in the Pacific. So they were available to go in the Atlantic. And other resources from Europe and so on were available from the Atlantic. But most of the people during that period knew that the Western Pacific was more important for the global climate than the Atlantic. But this political pressure moved it over there, and so it ended up being in the Atlantic. And Colin Ramage was one who was very upset about this. He's from the University of Hawaii. But also Japan, for example, they pulled out of GATE because they wanted to be in the Pacific. And so it happened in the Atlantic, but still, it was a very significant experiment. Many new results came out about convection, easterly waves, dynamics, and so on. That was a very important experiment for that. And so that was, GATE was one of the experiments along this path of the GART, with charting and vision. And then there was a follow-on called MONEX, both winter and summer MONEX, in the late 70s. And they were designed to investigate the monsoon, both in winter and summer. And those were really significant experiments also. They just had their 25th anniversaries. Anyway, so, and then there was the global FIGI, which was the year 1979 when there was global enhanced measurements. So I think that's a track there. But since then, there have been many others. I don't know, I mean, like in the 80s, there's EMEX, Equatorial Mesoscale Experiment, Australia, AMEX, and PAMEX, 1987, and STEPS, which was one of the Tropospheric Stratospheric Exchange in the late 80s and so on. And then going in the 90s, early 90s, we had TOPOCORE. So we've had just a tremendous number of field programs in the tropics, and each one has really provided some new insight.
I always have a question for this tropical convection contribution of energy, seismic energy, and compare with the hurricane, the whole world, how much the percentage?
How much does ordinary tropical convection contribute versus hurricanes?
No, not compare. Because hurricane is a little bit off the tropic.
Yeah.
Your count is probably a little bit. Hurricane was counted into the tropics, right? When you talk tropical.
Yeah. Okay.
Because the hurricane travel from the boundary into up higher latitude. So just for the comparison, how much?
Well, it's been estimated that if you ask the question, how much rain do hurricanes create versus all tropical convection, that's a calculation that's been done. It's about 2%. 2%.
So much less.
Yeah. So hurricanes don't. Yeah. I mean, they have other effects, but in terms of the total heating, because there are not enough of them, and they cover small areas, but convection is going all the time.
That's right.
Now, there are some who argue that the hurricane will affect the ocean.
Thank you.
同学没有问题，有问题的话，老师可以帮你翻译。
Considering the inverse of the heating profile,
right.
This is the vertical gradient of theta on the PV analysis. And this is actually also a boundary condition problem, right? So I just wonder if you can talk a bit more about the treatment of the boundary condition when we analyze the PV budget based on observation data and model output.
The boundary condition.
Yeah.
Well, what I've described here is is heating away from boundaries. I'm not quite sure what the question is, but the idea. I mean, there are other ways of viewing this, and maybe you're thinking about this approach of Haynes and McIntyre, where you have theta surfaces might intersect the Earth. Okay, and if there are no sources along those boundaries, then these concepts can apply. But what I'm talking about here is you have a stably stratified atmosphere with theta surfaces quasi-horizontal, and then you impose some kind of a heating. And it's really the vertical structure. There are various ways to view this. There's another one, Haynes and McIntyre, where you think about mass going across theta surfaces. And if you have divergence of mass across theta surfaces, then there has to be a convergence into that region, and so on. That's another way to think of it. But basically, it's the stratiform regions that have the strongest vertical gradients, so they have a bigger impact on the PV field. And also their horizontal dimension is several hundred kilometers usually. So you can think of them as in terms of PV dynamics, where there may be some quasi-balanced aspect that develops, of the flow that develops.
The radar can really see distribution of the clouds, but the satellite normally can only see the top.
Right.
So you show some evidence, but any specific information about the percentage of the so-called congested middle clouds? That is like a kind of convective, vertically convective congestions, or just ice cloud in that level?
Right. They have looked at this with the CloudSat, for example. And it's true, the CloudSat will just see the cloud, and there's attenuation. Even with the congestus cloud, you might have attenuation. And actually, what they're doing is combining these observations with the TRIM precipitation radar to sample the full column precipitation plus cloud. But some of these cloud peaks and mid-levels may be layer clouds, okay, that are there maybe as a result of melting or some residual cloud layer near the melting layer. But not all of these clouds, are at the melting level. These peaks, they're at a little bit higher. And if you look at some of those actual images, you can see there's vertical development, that they're actual, clouds that extend down to the boundary layer. And so there's a combination there of cloud layers plus individual cloud elements. And they're working to try to sort this all out. This is very preliminary. There's also cloud overlaps and things. It's very complicated.
Question about, you mentioned about that trimodal, like a trimodal cloud population in tropics. How about in the middle latitude? You have also NCS, and do you see that kind of trimodal?
Yeah.
Sysmex. How about the Sysmex?
The Sysmex? Actually, we see it as Sysmex, but that's not really mid-latitude. You're talking about like 40 north and so on.
Yes.
Yeah. We haven't really looked at that as much there. I think there are certain regions where it seems to dominate more, but one of from the CloudSat so far, the results that I showed here are only over water. Over the ocean areas. They're working on a technique to fly over land. But at mid-latitudes, I think these clouds are perhaps a little less common because of the strength of the surface forcing. You have the daytime heated boundary layer, for example, and the clouds have a lot of energy, a lot of cape, and they can just pass right on through. But in the tropics, if you look at the sounding, the cape is, the positive area is very weak, so the clouds sort of struggle to grow, they entrain, and they finally go up, and they can't go any higher. And also the wind shear is weaker, so they don't organize into rotation and strong updrafts, undilute cores, and so on. And so they also, because the wind shear is weak, they load up with precipitation, and that squelches the updraft growth. So the tropics, I think, you're going to see this more because of the weak cape, weak vertical wind shear. Mid-latitudes, probably not as prevalent.
So that means these should be included inside the convective scheme. I mean, the cumulus convection scheme, right?
Well,
it's so different between the tropics and mid-latitude.
Yeah, I don't know. I mean, presumably, if you want to have a continuous parameterization scheme that includes all cloud systems, if you think that's going to be important for, say, climate, then you probably want to include these. Now, obviously, the shallow cumulus probably have the same cloud dynamics as the congestions. I mean, congestions just grow higher. So if you have some kind of parameterization scheme that can include these kinds of cloud systems, but they're probably distinct from the deep convection. So maybe a parameterization scheme that works for the deep convection may not work so well for the shallow clouds, because these shallow clouds are such small areas, and I think they behave maybe somewhat differently. So, but I think if your goal is to get the atmospheric structure right, the humidity field, and so on, then you probably need to include these. Now, there has been a modeling study published by Pete Innes from Reading, where he used the Hadley Center model, and he did a simulation of the MJO with coarse vertical resolution, and he did get the MJO correctly. He also did not have mid-level clouds. Then he increased the vertical resolution when he resolved the staple layer, was able to get mid-level clouds, and he got a much better simulation of the MJO, suggesting this moistening process is important.
He mentioned there is a diurnal effect of the convection over the tropics. So how can we parameterize this kind of effect into a model? Because right now we don't take care of such kind of effect into the cumulus parameterization schemes. Do you have any idea how to incorporate?
I mean, for a climate model, say. Because, I mean, if you're modeling on shorter time scales, you have the diurnal cycle in there. But you're saying that's true. If you have if you're running a model for a 100-year simulation of the climate, how do you represent the diurnal cycle? Well, I think it's an important issue, because if you just say use the mean solar heating, you're not going to get the same cloud field that you would if you have the diurnal cycle. You're going to get more amplification and growth in nature in the afternoon. So somehow this nonlinear process has to be included, and I think it's a challenge. I don't know exactly how to do it.
Okay. Anyone other? Yeah, I have a question. From the scientific point of view, what is your personal perspective for the CAMX2?
Well, CAMX2, let me first say that CAMX number 1, almost 20 years ago, was focused on convection over the northern part of Taiwan and studied mostly convection along the coastline and over the water with the dual Doppler radar and so on. One thing we really missed was what's the structure over the land, so we did capture that. And also, we didn't get anything about convection in southern Taiwan. Yeah, so we missed that. Now, to me, and the US scientists are interested in CAMX2 because we're interested in flash floods. They occur in the US. But if you want to set up an experiment to study flash floods in the US and you put out a network, you'll never get the flood.
Yeah.
But in Taiwan, you always frequently get very heavy rainfall. So it's a perfect laboratory to try to study flash flood. You can set up a network and you're probably going to get a few cases. Now we've looked at some of the precipitation climatology. Some years it's dry. Okay, so can you tell us that in 2008, is it going to be a good year?
For the local circulation process.
Yeah, local circulation.
有没有其他问题 ？Professor Johnson， 我刚刚忘了介绍，他其实在算 Q1 跟 Q2 这个，从这个部分非常有名啊。你看他的 paper， 如果在计算 Q1 跟 Q2， 然后从 Q1、Q2 来了解天气或者中尺度的过程，甚至连接到对流尺度的东西，Professor Johnson 做了非常多的非常有名的 paper。I just say your contribution to Q1 and Q2 OK， 好，
是。
OK， let us thanks again for the